very quickly, am I pronouncing osda correctly? Or do you call it OSDA?
OSDA.
OSDA. Sorry
yes.
about that. Showing my ignorance.
That's fine. Yep.
Please continue.
All right. Good morning. Thank you for the introduction. So in the previous talk from Dr. Haddon, we've seen the potential of having the right catalysts to perform the right chemical reactions. And now I'm going to give you a perspective on how can we design these catalysts from materials, from the materials part of it. I worked with Professor Rafa Gomes-Mombarelli here in the Department of Material Science and Engineering at MIT, and today I'm going to talk how we're combining graph theory to material science to discover new zeolites. To put that in context again, 40% of the energy consumption in the US is due to the industrial sector. Of these, 46% is due to the chemical and refining industries. Basically, these industries are converting feedstock into high valuable chemicals and fuels. If only we knew how to convert, how to enable any given chemical reaction, then we would be able to significantly reduce the amount of energy usage from these industries. Protagonists among these catalysts which enable such chemical reactions to take place are zeolites. Among their applications, not only in catalysis, but also in gas separation and ion exchange, they move trillions of dollars per year in products. And this is only possible because zeolites have a very unique crystal structure. So they're very robust under harsh operating conditions, and they're formed by 4 connected silicon or aluminum or other heteroatoms in a very particular way, in a structure which has low framework density and these nanometer-sized pores. So such pores allow zeolites to work as very selective molecular sieves. So if one thinks of all possible ways of creating such a topology within crystals, then obviously there's a lot of different combinations. And indeed, computer enumerations predict millions of different thermodynamically accessible zeolites. The problem is that in practice, only 245 different zeolites polymorphs have been observed experimentally. The big question is, what makes a zeolite feasible, and how do we control the problem of zeolite polymorphism? If only we knew how to control these problems of polymorphism, then we would be able to tailor-make zeolites to certain given chemical reactions, which is the holy grail of catalysis. So here I'm going to talk how we're proposing the use of kinetic phase transformations to control the zeolite polymorphism. And backed on exhaustive literature search, we show how structural features are not enough to predict such transformations. Instead, our proposed graph metrics predict quite well such kinds of diffusionless transformations within zeolites. So to begin with, what do I mean with transformations? There are some certain chemical processes which transform one zeolite framework topology into another. For example, recrystallization processes usually based on hydrothermal treatments in which you break down a zeolite into smaller pieces and reassemble it into a new framework. A second way of thinking about this is through competing phases in which 2 different zeolite frameworks are achieved through the same synthetic process. Then we have what we call diffusionless transformations, encompassing reconstructive and topothetic transformations. We call them diffusionless because of their similarity with martensitic transformations in material science. They involve, for example, bonds being broken and reformed with low diffusion of atoms inside these crystals and unit cells. And also topothetic condensation of, for example, lamellar precursors to form 3D structures of zeolites. Finally, one last interzeolite relationship we found is the zeolite intergrowth, which relates 2 different frameworks through a stacking fault in the same crystalline material. So now that we know such transformations, what we need is actually, given 2 arbitrary zeolite frameworks, ideally one of which you want to achieve, how to predict if there is a transformation between these 2 frameworks. And if there is one, which transformation is that? When we go to the literature to analyze these problems, this is what we usually find. We find a library that each zeolite is composed by smaller composite building units, and these building units span a library of possibilities to assemble zeolites. And then the hypothesis in the literature, usually called the common CBU hypothesis, is some kind of Venn diagram in which two zeolites can be interconverted if they share the same common building unit. Our question is this a good way to design a zeolite transformation? And to answer that question, we teamed up with Professor Olivetti here at MIT to gather the largest data set on zeolite articles from the literature. So by extracting more than 2 million papers on material science using natural language processing and analyzing more than 70,000 articles on zeolites, more than 200 reports of interzeolite transformations were found. And to sum up the results related to the common building unit hypothesis, we found that 70% of the recrystallization processes do not agree with that hypothesis. So when we analyze from the perspective of framework density, it doesn't work as well. So if these local structural features are not good predictors of such transformations, would topology of the zeolites instead be a good prediction of how to convert zeolites? And to go to that world, we resorted to graph theory and started representing zeolites as graphs. To do so, start with a crystal structure, take each silicon atom as a node of your graph, and then oxygen bridges, like bonding two different silicon atoms, as edges in these graphs. Then you impose the periodic boundary conditions in your graph by looping back chemical bonds inside the unit cell, ending up with a periodic graph just like this one shown here. Now the question becomes another one, which is, okay, I have graphs for each one of these crystal structures. How do I compare graphs? And one of the most natural ways of doing this in the graph theory is through the graph isomorphism. So two graphs are said to be isomorphic if they differ just by relabeling of their nodes. That is, if they're equivalent under certain permutations of nodes. Analogously, we're expanding this concept to crystals by saying that crystals are crystal graph isomorphic if they share the same graph representation. So if every single zeolite topology were unique, we wouldn't find two zeolites sharing the same graph representation. But to our surprise, we found 14 pairs and one trio of zeolites which share the exact same graph representation. That is, when boundary conditions are taken into account. And this is quite interesting because some of these zeolites are actually related by transformations. Take the example, of Gmelin zeolite converted into AFI zeolites upon heating. This is the process that happens to that crystal structure. You heat up Gmelin, you shrink the C direction of each unit cell, break some bonds, and reform them. But you do it in such a way that the bonds which are broken are reformed with the same atoms when the periodic boundary conditions are taken into consideration. So these two crystal structures share the same graph representation. And why is this meaningful to us? Well, that is, if two crystals share the same graph representation, it would imply that there is a lower barrier to interconvert such crystals, because not only they have the same number of nodes inside their unit cells, not only they have the same number of bonds inside their unit cells. For each atom in one crystal, there is one equivalent atom in the second crystal with the exact same neighborhood. So it means we could analyze and we could induce such diffusion-less transformations within these materials just by looking at their connectivity. But the problem is that the graph isomorphism is not a very precise way of comparing zeolites, and I can explain why. It's not the graph representation is not invariant to the choice of the unit cell. So take the simplest example here, which in a 1D lattice, and make different graphs for each one of these supercells. You end up with different graphs. Now, if you compare them using your binary metric, which is the graph isomorphism, they're going to be different. So we want to bypass these problems and to compare graphs or crystals in a more fair way. So say you're given two crystals, crystal A and crystal B. You could map these crystals directly using by their primitive cells to their graph representations. But this is, as we saw, not a fair way of understanding these comparisons between crystals. Another crystallographic way of seeing that is, instead of taking their unit cells, take a supercell of each one of these crystals and map the supercells to graphs under the restriction that both graphs must have the same number of nodes. Now we're comparing graphs with the same number of nodes, and that's more interpretable. Here, compare, for example, graph of the supercell A with the graph of the supercell B. We see that the only difference between those two is that graph A has 2 extra edges here. Understanding and interpreting these results from the transformations perspective, it means that to convert crystal A to crystal B, we first have to break these 2 extra bonds inside the transformation, and then distort the lattice in diffusionless-like transformation to achieve crystal B. Now, if we apply these reasoning to zeolites and compare it with all the results we found in the literature for such diffusionless transformations, we found that our graph metric explains all but one the results of the literature of diffusionless interconversion. In contrast, some other descriptors which take into account, for example, common building units or framework density into a single metric of distance, structural distance, is not as predictive as the graph similarity. But most interestingly is when we plot these two informations here in the same XY plot. Here in the x-axis, you have the graph distance between 2 zeolites, and the y-axis, you have the structural distance between these 2 zeolites. And each one of these points is an experimental observation of a zeolite interconversion. We see, as I mentioned before, that all diffusionless transformations represented by these red dots here fall on the low graph density part of the plot. Sorry, graph distance part of the plot. All but one, and there's one single exception, which is the LTA-IFY transformation. It requires an external stress of 3 gigapascal, however, to make this transformation work. It means that the graph similarity metric can fail as long as the conditions to make these transformations are very extreme, such as the application of these 3 gigapascal external stress. So if we look for all pairwise combinations of known zeolites which have very low graph distance, then we find more than 230 pairs that fall on these regions. It means that all of these 230 pairs might contain pairs of zeolites which haven't been observed within such transformations, but in principle could be realized through such processes. So this may open a line of research to investigate whether we could achieve such zeolites with very custom silicon to aluminum radio without the use of organic structure directing agents and so on. Finally, if we analyze not only the graph distance but also the structural distance, we see that all cases of zeolite intergrowth fall on these 2 regions of these plot. That is, zeolites that can be grown together, they either have very high graph similarity or very high structural similarity. And so, again, when looking at the all pairwise combinations of zeolites that fall on these regions of the spectrum, we find more than 130 pairs of zeolites. This means there are lots of pairs here waiting to be synthesized and tested in order to form, for example, composite catalysts with dual properties, each property of one of the frameworks. Finally, if we go to all those databases of hypothetical zeolites, that is, zeolites which have been enumerated by computer predictions, we found more than 3,900 zeolites which are graph isomorphic to known ones. This means that for each one of these hypothetical zeolites, we pointed one known zeolite, which can give us a clue on how to make these hypothetical ones. And this opens a new venue to synthesize zeolites faster and in a theory-guided way. So to sum up, we based ourselves in an exhaustive literature search to propose kinetic phase transformations as a way to control zeolite polymorphism. We have shown how structural similarities are not enough to predict such transformations, and rather how graph similarity is a good way to predict zeolite diffusionless transformations. With that, I thank you for your attention.
So for those of you who've shared sessions, you probably appreciate how grateful you are for the speakers, unlike my presentation this morning that finished with a little extra time. So thank you. We do have time for questions.
Yes, thank you. So I'm curious if this graph technique, and in particular, the desire to be able to look at different structures and try to quantify the difference. Now, what you've done is you've generally looked at the difference between periodic structures.
That's it.
But could you also look at the difference between, for example, a known periodic structure and a disordered network, like something kind of representative of the synthesis gel that's actually leading up to the zeolite, and try to quantify the sort of distance or the difference between those two structures?
Yeah, so absolutely, we can do it for non-periodic structures. So for example, in the molecular world, this is very common. This kind of graph representation is very common. For amorphous systems, we haven't seen we haven't applied these techniques yet, but indeed, during the synthetic process, it's very desirable to understand step by step the formation of a zeolite. So in our next project, we're interested in doing exactly that, but from the perspective of synthesis and clustering around molecules, for example.
So fascinating work. All these are temperature-driven or stress-driven transformations, the known ones.
Among known zeolites, the diffusion-less transformations are usually stress or temperature-driven.
But
yes.
are they more temperature or more stress-driven?
We have more reports of temperature-driven diffusion-less transformations than stress-driven ones. But as we have seen, it might require a lot of external stress, huge external stress, in order to induce these phase transformations.
And when you define the geometric similarity, do you take into account the strain in the supercell?
No, the strain reflects on the graph representation. So for example, how close are silicon atoms together? So in order to map a crystal structure to a graph, we used in the zeolite language oxygen bridges as a definition of bonds. But then if you go to more complex systems or strained systems, you might have extra bonds. Like the atoms might not be exactly connected because they're in these like intermediate or transition state between two polymorphs.
Thank you. That was a really fascinating talk.
Thank you.
I don't want to put you on the spot, but okay, I will. How applicable do you think your natural language processing system is to reviewing other areas of the scientific literature? Say sort of the properties of enzymes, for instance, for gene function annotation. Do you think the tool is generalizable, or is it something that's very specific to this type of problem?
Mm-hmm.
Go ahead.
Thank you. The tool was actually developed by Professor Olivetti and her group. They have a couple of lines of research dedicated to analyzing synthetic recipes, for example. Based on a series of different materials, how do you design a certain material given all the prior knowledge from the literature? So,
oh, that's fascinating.
Yeah.
Well, thank you very much.